Mechanical calculators may have faded from everyday use, but their legacy lives on in simple mechanical counters like this one. And if you look closely, you'll find the same counting mechanism inside your analog power meter, your water meter, your car's odometer, and even the counter on a hand gripper if you like tracking repetitions. Mechanical counters are essentially simple mechanical calculators that can only perform one operation: adding one. Each time the leftmost digit wheel completes a full revolution, it must transfer 1/10 of that rotation to the next wheel. This is the carry operation. In principle, this can be achieved using two gears, one with 10 teeth and another with a single tooth. When the one-tooth gear completes a full revolution, it advances the 10-tooth gear by exactly one tooth or one digit. To ensure the adjacent digit wheels rotate in the same direction, an intermediary gear is inserted between them. The exact number of teeth on this intermediary gear does not affect the gear ratio. It simply reverses the direction of rotation. In practice, if the digit wheel has 20 teeth, the carry gear may have 2 teeth, with an intermediate gear of, for example, 8 teeth. The specific tooth count of the intermediary gear is not critical, though keeping it smaller allows for a more compact arrangement. The gears can be packed together like this, and additional digits can be added using the same repeating structure. For now, let's focus on a 4-digit arrangement. The first digit wheel is attached to a carry gear. When it completes a full cycle from 9 back to 0, the carry gear engages a small carry pinion, transferring motion to the next digit wheel. If we look closely at the carry pinion, we'll notice that some of its teeth are shorter than others. We can also see that part of the carry gear has a smooth circular surface instead of teeth. These features are intentional. When the carry gear is not actively transferring motion, the smooth circumference and the full-length teeth mesh in such a way that they prevent the carry pinion from rotating freely. Without this constraint, the momentum of the carry gear could cause the pinion to overshoot, potentially advancing the next digit by 2 steps instead of 1. This carefully designed interaction ensures that each carry operation is precise and occurs only once per full revolution. Most mechanical counters use a variation of this same carry principle, except this classic mechanical tally counter. What makes this tally counter unique is the way it increments the digits. If we look inside, we immediately notice that the mechanism is completely different from the gear-based carry system. There are no carry gears at all. Instead, this design relies entirely on pawls and ratchets. When the count button is pressed, it swings this assembly that holds a series of pawls. Each click swings this assembly, allowing the pawls to push against the ratchet teeth on the digit wheels. If we examine the digit wheels closely, we can see ratchet teeth around most of their circumference, along with a small cutout section where no teeth are present. The pawls are arranged in different lengths. The longest pawl corresponds to the leftmost digit wheel, and it is always engaged with that wheel's ratchet teeth. This means every click directly advances the first digit. The shorter pawls, however, normally sit slightly above their respective ratchet wheels and do not engage. But when the first digit completes a full cycle from 9 back to 0, its cutout rotates into position beneath the first pawl. At that moment, the first pawl drops into the cutout. This downward movement lowers the entire pawl carrier just enough for the second pawl to engage the next digit wheel. As a result, the second digit advances by 1. Once the cutout passes, the first pawl rises back onto the ratchet teeth, lifting the pawl assembly and disengaging the second pawl again. The system resets automatically. When the counter reaches 99, 2 cutouts align at the same time. This allows both the first and second pawls to drop simultaneously, lowering the carrier even further, enough for the third pawl to engage and advance the third digit. The same principle continues. At 999, 3 cutouts align, 3 pawls drop, and the fourth pawl engages, advancing the thousands digit. No gears or carry pinions. Just a carefully staged interaction of ratchets, cutouts, and spring-driven pawls. But what about digital counters like this one? How do they actually count digitally? If you're curious about that, you might want to check out Brilliant, the sponsor of this video. Brilliant helps you excel in math and coding, with step-by-step interactive lessons and personalized practice. Learn by doing. If you want to understand how digital counters work, their digital circuits course is a great place to start. It goes from binary numbers to logic gates and shows how you can build things like counters, or even a simple CPU. The courses are designed by people from places like MIT, Harvard, and Stanford, and they're made for pretty much anyone, from kids to adults. Everything is explained with really clear visuals, and solving problems along the way just makes it all feel more intuitive and more fun. To learn for free on Brilliant for a full 30 days, go to brilliant.org/Quasar-Ed, scan the QR code on screen, or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. On the side of the counter, there is a reset knob used to return all the digit wheels back to zero. This knob is connected to a central shaft that runs through the digit wheels. Mounted along this shaft are 4 small pawls, each positioned to engage with its corresponding digit wheel. When the knob is rotated, these pawls catch the internal ratchet teeth of the digit wheels and drive them together. Because all 4 wheels are linked through the same shaft, they rotate simultaneously until they align at 0. Once the digits reach 0, you simply stop turning the knob. This pawl and ratchet mechanism allows the wheel to advance independently during normal counting without forcing the reset shaft to rotate. This one-way interaction ensures that pressing the count button does not spin the reset knob. There is also another set of retaining pawls that prevent the digit wheels from rotating backward. These pawls enforce one-directional motion and produce the familiar clicking sound as each digit snaps cleanly into position. Together, these mechanisms allow the counter to reset smoothly, count reliably, and maintain precise alignment at every step. Mechanical counters like this may look humble, but they represent a lineage of engineering that once powered calculators, odometers, and measuring instruments long before digital electronics took over. If you like learning how things work, subscribe to this channel and I'll see you in the next video.